your recording is on. Okay, and the sound, so recording is on, the sound is on. And now let me open the slides. Okay, so today on the agenda, as I said, it'll be performance metrics. So I'm going to, and also before I forget, actually, let's go back to Brightspace and just assign the homework. Okay, so I'm going to go to naive base, right? So we had, so the K&N homework, that was the last one that you submitted, right? And that was due. If you haven't submitted this already, you can always still email it to me. Okay, make sure that you complete that assignment. The naive base should be easier because you have the code, okay? So, and you have everything to test the performance. So I'm going to create a link here. So new assignment. Okay, so it'll be homework, naive base, and it's very simple. Basically, just run the code that I gave you, fix the errors as I mentioned. So this will be due. Actually, it's so easy, this homework, that it'll just be due a week from today. So let's make it the 24th. Okay, so by 10 p.m. Okay, so I'm just going to say run and print the results for the naive base algorithm we discussed in class, right? Which is attached, by the way. So pretty easy, just run that, make sure you get the results, the accuracy basically at this point. Does this make sense, guys?
Yeah.
Yeah? Okay.
Yeah.
All right, so this will be due, as I said, on the 24th, so it'll stay open until the 27th. Okay, so naive base, run and print the results for the naive base algorithm we discussed in class, which is attached. Okay, so that's in there. And if you look, if we go back to the folder, you will see that it is actually, here's the Jupyter Notebook, here's the Python version, so they're equivalent, and here are all the notes. So just make sure this runs and you can print out the results and run it basically. Okay, so that runs really well. I looked at it last week after you fixed that error with the square brackets. All right, so that's naive base homework. Then after that, you're going to have, as I said, a WEKA homework. This one will also be pretty straightforward, you'll see. But that's the discussion for today. So now I can go ahead and share. I'm going to share the slides. Share PowerPoint. Okay, and I'm going to start the slideshow here. So you should be seeing now the slides. So this is, what is this about, basically, right? So last week we were covering, we covered performance metrics, right? And we talked about the accuracy. So we talked about how we could measure the accuracy of something. Okay, so we had accuracy, right? And that was basically that we had Y-pred, right? And then we had Y-test. Okay, so that was the idea there. And so, if we had some values like 0, 1, 1, 0, 1, 1, 1, right? We have these match, these do not match, these match. Therefore, we calculate that we have 75% accuracy, right? And that's that's usually the first metric that you want to take a look at, but there are other metrics. Okay, there are other metrics. And today I will give you some code. It'll be on these slides that you can also incorporate into your toolbox, right? So you have, remember, you have this toolbox of machine learning algorithms. And so today you're going to learn, WEKA, which is a great tool that, it's such an easy tool. You can learn it in literally a day. And then some code also from, to calculate the other metrics. So we'll take a look at that. Okay, so that's the plan for today, and you can see it'll be pretty straightforward. All right, so the title then is performance metrics, and that's what it falls under. So far you guys should have a pretty clear understanding of accuracy, but possibly not of the other ones. So the learning outcomes here, students will have a better understanding of machine learning approaches, and better understand, I guess this should say, performance metrics. And this should say understanding of machine learning evaluation methods, really. Which is really just the focus of today. Given it's a short week, it fits in pretty perfectly here. So what are performance metrics? So, what are some of the things that we've been doing? So you guys, so far, we've been using a function called train test split, right? And we've used that one already. That's in the code examples that we've done so far. And basically what it does is it usually takes the X matrix and the Y vector, and it's going to split them into X train, Y train, X test, Y test, right? So that's really ultimately what it has done, okay? So, so determine how well, the objective of performance metrics is to determine how well a model performs on the data itself. And data is usually, we've been dividing it into train and test, but sometimes you usually also have another set called a validation test. And the idea is that you initially train with this, but then you kind of evaluate on this one to kind of tune the parameters a little bit better. And then once you've done that, then you apply your finalized model to the test set. So that is something that is done sometimes, right? That's another approach. So basically that means you can divide your data set randomly, right? You randomize all your data samples first, and then you divide into 60% for train, 20% for validation, 20% for test, okay? So that's really the plan there. Sorry. Okay, so, however, there are other ways of doing this. Another approach is something called tenfold cross-validation. Tenfold cross-validation, it's different from, let's say, the 80%, 20% split, right? So, you're not going to use that approach. Instead, you use the tenfold cross-validation. So 80-20% split would be this one. Tenfold cross-validation is that one. So the idea is that now you're going to take your entire data set, you randomize the samples again, right? And then you split it into 10 bins. So you split into 10 bins. Oops. And you split it into 10 bins, and the advantage of that is that now you're going to evaluate your model 10 times, whereas here you evaluate it only one time, here you evaluate it 10 times. And the way that you do it is that every iteration of the 10, you grab one. So you say, I'm going to hold this one out. So hold this one out as test, and I'm going to train on the rest. So I train on all the other models, and then I leave that one out as test. Then in the next iteration, you grab the next one. So I grab this one as test, and I train on the rest. Then in the next iteration, I grab this one as test, and I train on all the rest. That way, you're basically performing the same operation 10 times, but with different samples organized in different ways. And in general, then, you get 10 responses instead of one. since you get 10 different responses, now you can take, let's say, the average of those 10 responses, and in theory, your answer should be more logical, right? It's kind of like you go and you do something with your car engine, and you disconnect this and that, and you think, oh, I fixed it. But then you do that, and then you try something else, and then you try something else, and different random parameters. And then by doing that, you just have a better picture of what you're doing, okay? So that's the idea, in this. So that's called tenfold cross-validation. It's something that we will see today in the WEKA tool, okay, that we can do it. And obviously we can do that in code, but so far in the code, all we have been doing is the 80%, 20% split, right? That has been our approach. But now we are introducing this idea of tenfold. The way that we calculate accuracy in the performance metrics does not change. So that's still going to be pretty much the same. All right, so here are the metrics, some of the common metrics that are used in machine learning and deep learning. Okay, now there are other metrics that are used in things like reinforcement learning or in linear regression, other metrics that might be used if you talk about language translation. There's other different types of metrics, but in general, for supervised learning, for classification and supervised learning. So this is for classification problems. And, particularly supervised learning. If you remember, this is from the classifications that we talked about at the beginning of the semester, which were supervised, unsupervised, and reinforcement learning, right? So out of those three, these are the metrics for supervised learning. As you know, supervised learning is one of the most important ones, although in a couple of, although I should say, it's supervised learning is not all that we cover in this class, right? So we'll cover unsupervised learning. Actually, next week we're covering recommender systems and singular value decomposition, which is a different kind of thing from the standard supervised learning. And then after that, we're covering reinforcement learning. So really so usually at this point in the semester, right around the exam, we kind of finish with supervised learning and traditional. So in a sense, I should say, you should feel good about the fact that we've just finished one specific block of machine learning, right? So one specific block of machine learning, which is the supervised learning, classification, traditional algorithms, because we saw naive Bayes, we saw KNN. There's also decision trees, but there just isn't enough time. So if I have time at the end of the semester, I would cover it. But now, we finished all of those. We've gone through them very carefully, and we kind of wrap it up with WEKA, which allows me to introduce at least a way for you to use decision trees, even though I may not be able to discuss the algorithm quite yet. Then after that, if you remember, we will cover recommender systems, then reinforcement learning, which I think this one you guys will really like because it's the thing that has to do with like self-driving cars and all of that. We'll do the taxi cab example. And so I'll give the intuition for that. And then after that, we'll begin the really big gorilla in this class, which is neural nets. Right? And there's a lot that goes into neural nets, which actually includes a little bit of linear regression and logistic regression. So we'll talk about that. And then finally, we wrap up with unsupervised, hidden Markov models, and anything else. We have, GMMs if we have time. All right, but my point is, feel good about the fact that we've wrapped this up. We're basically closing up this part of which is a really important part of a machine learning course. Of course, we'll continue to use NumPy throughout, and a lot of these tools we will, and neural nets are related to supervised learning in some way, so we'll come back to that. And these performance metrics, we'll continue to use. All right, so that's the idea. So far, you should understand accuracy, right? So we've covered accuracy, but now we're going to introduce a few other metrics. We're going to introduce precision, recall, something called the F measure, the confusion matrix. The ROC curve is another metric, but I'm not going to have time to cover that one today. So if time permits, maybe at the end of the semester also, it would be a topic. But these are the main ones if you're ever having to do a report of any kind, right? So if you ever have to do a report of any kind, or you have to do a research paper or anything like that involves classification and supervised learning, you will need to report these metrics. Okay, so today I'll just show you a really quick way that can be done. That is actually pretty easy to understand. All right, so that's what we're going to talk about today. So then we can move on to evaluation, right? So the performance of classifiers, so the evaluation. Now to do this. Although you did the accuracy by hand, you learned how to calculate accuracies by hand. Going forward, we will just simply use sklearn for this. So today I will give you, obviously I'll give you the intuition of how everything works, but basically the code will just utilize the built-in functions that we have for this. All right, so we will use the sklearn metrics module. So I've already introduced sklearn in this course, right, last week for something, for the split, train test, and also for the data sets, right? Whenever we wanted to get a data set, I showed you guys how that works. So we will use the sklearn metrics module for performance evaluation of the classifiers. I will show how this model can be used with sklearn classifiers, or NumPy classifiers, and later on we will see that we can also still use it with other frameworks, related, like if you use PyTorch or you use TensorFlow, etc. later on in other courses, you can use it basically still. And this will help to more easily understand how to evaluate machine learning. Since we don't have to use the more complex and very verbose, other things. So I guess this should say the NumPy, right? So disregard this whole paragraph. So basically what I'm saying is, you can use this with everything. You can use this with, as long as you're using Python, really, whether you're writing your code from scratch in NumPy, which is kind of my goal with this class, to all the way to using the built-in sklearn or TensorFlow, you can always use it pretty straightforwardly. And the approach, if you understood the accuracy function, this will be even easier to understand, okay? Because this is more sort of built in, okay? So in sklearn, the functions are called accuracy score, recall score, F1 score, precision score, and confusion matrix. And basically, I have already written a function that you can just plug in. Just like before, we wrote the accuracy function. This time around, I've already done the function, and it's here in the slides. So you can literally just either type it up in your own libraries, or you can just copy paste it from here. So before we get to that, before we get to the tools, we have to go through the idea of what the metrics are. All right, so please, if something is not clear, make sure you ask questions, okay? But, because this can be a little bit tricky sometimes. But I do have an example after this to help drive it a little bit more. So what is accuracy, basically? So because we've already done it from scratch with NumPy, you should understand it. But basically, we have the following, right? We have a table, and the possibilities, this is for a 2-class problem, but obviously this would extend to 3 classes. So the idea is that we have, of course, data that is the real data, right? So we're thinking of the test set here. So this is in terms of the test set, right? Because that's usually where we do our evaluation of our models in the test set. So in the test set, what do we have? We have the data. That's called the true data. And for a two-class problem, we're going to have true ones and true zeros, right? Then on the other hand, we have what the model gives you. So this is what the model, the trained model, will do. Predicted 1 and predicted 0. So for every test sample that we know what it is, you know, the true 1 and true 0, the model will grab it without the labels and say, oh, I predict this to be a 1, I predict this to a 0. So then we end up with these 4 possibilities that can happen, right? So if we take a sample, we assume it's a true 1. If that sample is truly a 1, the model could either say that it is a 1, or it could incorrectly say that it is a 0, right? So that's why we have A and B. The same applies for the other one. We have over here, we have a given sample and we know it's a true 0. The model, once again, given that sample without a label, could predict incorrectly it is a 1, or correctly that it is a 0. So these are basically the correct ones, and these are the incorrect ones. These are also called true positives and true negatives, and we'll mention that in a second. Okay, but the idea here is that, you know, if it's a true, then you would want the model to predict it as, if it's a 1, sorry, you would want the model to predict it as a 1. If it's a 0, you would want the model to predict it as a 0. And if it's, you know, and so if it's a 0, you don't want the model to predict it as a 1. If it does, that is incorrect. All right, so to calculate the accuracy then, given this table, we can calculate the accuracy by saying, well, I just add A plus D as the numerator, and then I add all the rest, A, B, C, D, as the denominator. And that's basically your accuracy. And that's exactly what we've done as we've done other examples of this, right? So that's the exact same thing. Questions?
Makes sense.
All right, so now we get into these other metrics, precision, recall, F metric. Now the beauty about these is that they all use the exact same table, right? They use the exact same table. And sometimes you want, you know, I'll give an example that kind of drives this a little bit better in a second, but accuracy is not always the best metric. It's not always the best metric, in particular, when we have a data set that is highly imbalanced. Right? And what that means is that we have, for instance, two classes, 0 and 1, but here class 0 is 98% of the data, and then class 1 is only 2% of the data. So this can happen, for instance, in things that are very infrequent, like fraud, right? Fraud is not, you know, there's millions of transactions, not all of them are fraud. Only a very small number is fraud. Or, you know, any kind of exception that you have, you know, and I'll give an example about terrorism. You know, out of millions of people that travel in the world, right, there were, in the last decade, there were, or since 9/11, I guess, there were about 19 or 20 actual terrorists. So out of millions, right? So think about how tiny that is. So basically, you could just build a classifier that makes everyone a terrorist, right? Or not a terrorist, and it'll get very high accuracy. But the precision and recall will be very bad. Okay, will be very bad. So here we take a look at that one. So precision basically means what? If we look at the denominator, A and C, that's basically these two, right? So we're saying that out of all the values that the model predicted, out of all the things that it identified as whatever, the thing that you want, right? How many of those, A, how many of those were actually true? Okay? So you can see out of all the ones that it predicted as 1, how many of them were actually 1? Because that, you know, that is a better metric, you know, in terms of what you might want there, right? Because it's looking at, out of all the predicted ones, well, you'll want a high number there for A. Now the same thing, now if we look at recall, recall is the other metric. Now here we can look at the denominator is A and B. So that's going to be this one. So this is going to be not out of all the predicted, but instead out of all the true ones. So out of all the true ones, right, you know, how many did the model capture? Right, so it's different, right? So these are two different things because this one doesn't miss anything, right? So this one would, you know, out of all the correct ones, you know, for instance, if you think of cancer, right? Cancer diagnosis, you want to be very accurate there in your model, right? So you would want your model to capture all of them and not miss any. So these are the ideas that you have to think about, you know, when you're deciding, okay, I'm building a model, but should I be using accuracy? Should I be using recall? Should I be using precision? Right? So which one of those is the best? And that's why what I will say is that whenever you do a machine learning project or report or, you know, research paper, you really want to present. You really want to present all the metrics. So you want to present the F measure, the accuracy, the recall, the precision, and then one more thing called the F measure, which we will see in a second. All right, so again, precision is, recall then is out of all A and B, so out of all the true ones, you know, how many were actually one? All right, out of all the ones, how many actually were one? Which is the thing that you wanted. Was that, you know, very tiny or very big? So is it finding a lot of the data? So the difference between recall and precision sometimes is that one of them will find more noise. And so what is it that you want? Do you want a lot of noise but to find everything, right? So do you want something that's really huge but that definitely includes what you want? Or do you want to miss a lot, right? You want to miss a lot, but out of all that you capture a lot of what you want. You see that? So, you know, it's kind of like that. So it's a trade-off, right? So in one case, you capture everything, but there's a lot of noise. In the other one, there may be a lot less noise, but a lot of what you captured, which is this, so is the thing that you want, but you're missing a lot of it. So you got to think of it in those terms. So that's why you have to really analyze which metric it is that you want. Questions?
No questions.
No questions. All right. So now there is a metric called the F measure, which is this one, which we will look at in a second. But the F in more detail. But for now, let's just say that the F measure is a metric that allows you to combine precision and recall. So if you look, its F measure is actually made up of precision and recall here, right? So it's what it's called a harmonic combination, basically, or a harmonic mean of the information, okay? And this one, the F measure, actually is something that whenever you report that, if so, let me put it this way. If you just want to look at one metric that captures how good your model is, it would be the F measure. If you only had time, let's say, to look at one, then you would look at the F measure, because if you have the higher the F measure, the better your model is overall in terms of precision, recall, and accuracy. And so this is going to be like the combined metric to look at. In a second, we will take a look at it. Obviously, we need to look at the table here to calculate recall, then again, the table to calculate precision, and so on. And then from there, combine it to come up with the F measure itself. The other metric that we can take a look at is called the confusion matrix. And we will see this when we look at WEKA in a second. All right, today. So I always, in every course I do, regardless of what it is, I always show WEKA because it, as I said, it's a good calculator, right? So it's a good calculator to have next to you so that you can always compare your algorithms. You can always, even if you're using big data and WEKA just doesn't have enough memory, you can always just take a sample of your data that's the biggest that you can fit into WEKA and run it, right? And just get a feel for what's going on in the data itself. So in WEKA here, we have, so in WEKA, basically what we have is, we have this table, right? We have this table here, and this table shows, again, you know, out of all the classes, we're taking here the iris data set, iris, right? Which, as you know, has 3 classes, Setosa, versicolor, virginica, and it basically, the confusion matrix just shows how they're being classified. So if it's an A, how many were classified as A? Well, 49, and 0 and 0 were misclassified as B and C. So that's great. The model's doing well there. Now, when you do versicolor, 40, which is B, right? So 46 samples, this is from the test set, by the way. 46 samples get classified correctly as B. But then there are 4 B samples that get misclassified under the C column. Okay, and that is, of course, a bad thing. That's an error. But it's not too bad, right? So it's only 4 errors there. And then on the other end, virginica over here, you can also see the same. Virginica is C, and in 46 were classified correctly as C, okay? And only 4 were incorrectly classified as B. So as you can see, there is no confusion for A. The system somehow, the features identify A really well. But there's a little bit of a problem in classifying B and C. So there's a bit of an issue there. So whenever you do more of your feature engineering, more of your research analysis, you would probably try to figure out why is it that versicolor and virginica are harder to classify, right? So that's where you would focus your attention to improve your model. Obviously, with iris, things do really well. With other techniques, this will be, you know, you'll have more errors, of course, with other data that is more noisy, where you don't have that, you know, great features, etc. You can expect your data. So what I'm saying is, rarely does real world data look like this, right? So this is more of a, you know, for teaching purposes, iris and this can have really good results. Okay. All right, so that's the confusion matrix. Now, the second part of this discussion is to do an example. So let's call it round 2. Basically, I'm going to repeat everything I just said, but this time around, I'm going to repeat it with an example, okay? So I'm going to repeat it with an example. All right, so let's consider, because this is really what you would have, right? You would have this in your, you know, you ever take a project that you're working on, this is what you're going to have. You're going to need some context, right? About, okay, what is the thing that I'm trying to figure out? Okay, if I report accuracy, is that really correct? You know, all that. So let's take a look. So let's say, would you believe someone who claimed to create a model to identify terrorists trying to board flights with greater than 99% accuracy? You know, so obviously if you went to the, you know, the Pentagon or Homeland Security or something like that, and you say, hey, I have a system I can sell to you, to your airports. It's got 99% accuracy. Think about what you're saying there. That sounds pretty impressive, right? 99% accuracy. But it's 99% accuracy of what? That's, you know, that's the big piece of it, right? Because accuracy here is not a great metric for what we need. You know, think about it. So here's the model. Basically the model, simply label every single person flying from a US airport as not a terrorist. Would that be accurate? Sure, right? You know, the majority of people that fly are not terrorists out of millions and millions of people in the world, right? Only a handful. And so if you label everyone as a non-terrorist, yeah, your model is going to be accurate. And it's going to have very tiny error for the 19 that were terrorists and they were misclassified as non-terrorist. However, the Pentagon or whomever, the FBI, they're not going to be very happy, right? Because, you know, what they want is to find the terrorists. So that's the problem, basically. So given that, you know, 800 million average passengers, you know, given the 800 million average passengers on US flights per year, and the fact that there are only 19 confirmed terrorists who boarded US flights from 2000 to 2017, think about that. The numbers are astronomical here, right? So 800 million versus what, 19? So obviously your model does really well if you have a model that is, you know, 800 million out of 800 million and 19, right? So yeah, if all of those are non-terrorists, the model does really well. But the problem is the model does not find the 19. And that's really what you want. You want those basically like anomalies. So that's really the kind of the argument for not using accuracy here, because accuracy does not really provide the information that we need. So this model achieves an astounding 99.99999% accuracy, right, for detecting non-terrorists. And that might sound impressive, but you know, Homeland Security may not be calling anytime soon to buy your model, which is, you know, that's a bummer. So while this solution has nearly perfect accuracy, this problem is one in which accuracy is clearly not an adequate metric. Okay, so not an adequate metric, which is what I just said. So the terrorist detection tasks, just like many tasks out there, are what are called imbalance classification problems. And as I said, imbalance just means that we have two classes that we need to identify, but instead of having, you know, 1,000 and 1,000, you know, imagine if there were only 2,000 people that flew airplanes and half of them were terrorists, right? So that would be convenient for machine learning, right? So machine learning would really want that because it wants balanced data sets. But unfortunately fortunately, let's say in real life, but for the machine learning algorithm, certainly it's problematic because you end up with 19 terrorists versus 800 million or so, you know, a lot. So this is highly imbalanced, and it's a very challenging problem for machine learning, right? Very challenging. So one category represents the overwhelming majority of the data. Other imbalance classification problems occurs in disease detection, right? So out of all the cases, only a small percentage, you know, would be, even with COVID nowadays, right? So it's, you know, 100 patients and maybe 10 or whatever, probably less than that. So basically the idea, the diseases could also be low in the public. In both these cases, the positive class, disease or terrorist, is greatly outnumbered by the negative class, right, non-terrorist, for instance. So these types of problems are, you know, fairly common, right? That you will encounter when accurate, and basically the conclusion is that accuracy is not. So basically the conclusion is that accuracy is basically not a good measure of assessing model performance, okay? So it's not a good measure for assessing the model performance. And so that's why we introduced the ideas of precision, recall, F-measure, and there's other techniques as well, like, you know, figuring things out beyond that. But for now, today, we're just focusing on the performance metrics, okay? So that hopefully this motivates the reason why we might need to look at other metrics. Okay. All right, so now intuitively, so now let's more intuitively try to understand here. We know that finding all negative data points in the terrorist detection problem is not helpful, right? So who really wants all the, you know, all the grandmas and grandpas, right? So that's not very helpful, right? So so instead, we should focus on identifying the positive cases, right? Whatever it is, disease or terrorists or whatever, in the stock market, right? So if you're interested in becoming rich, right, with a machine learning algorithm, deep learning algorithm, this is what you have to do, right? You have to increase that recall, or you have to increase that precision, because it ultimately translates into money, okay? So the metric, our intuition might tell us that we should maximize, is known in statistics as the recall, right? So maybe it's not the accuracy, but the recall that we want to maximize. So that is to say, so that whenever you were doing your machine learning and you're playing around with your features and your training and your samples and everything, you were trying to get an accuracy that was really high, right? But in these kinds of cases, now you have to say, no, you know what? I'm going to forget about I'm going to look at all my results in terms of the other metrics. Like, I'm going to forget about accuracy, sorry. And I'm going to look at all my metrics, and I'm just going to focus on recall or precision. So let's think about recall here, which, if you remember, recall we already define as being this one, right? So we already define as this equation here, and given the table that we have there. So we have the recall here. We can kind of define it as, or recall, the ability of a model to find all the relevant cases within a data set. So all the relevant cases, okay? So let's take a look at the table again. We're going to come back to the exact same table that I had before. So remember, I said I was kind of going to repeat everything. However, usually before I just use letters because I kind of like looking at things that way. But traditionally, you will see a lot, in either your statistics course, I'm sure you probably saw this, or, when, anywhere, any report online, blog, whatever, where you read about this, they usually talk in terms of what are called true positives and true negatives versus false positives and false negatives. Okay, so that they talk really about that. But it's exactly the same thing we had, right? So these are the predicted. Notice that also this is inverted from how I had it in the other table. So you have here what the actual is, the real data. Remember, this is the test set, right? Only the test set. So out of the actual, how many were the 0 class or the positive class, and how many, or the 1 class, I guess, and then how many were the negative or 0 class, right? So that is the actual. And then on the row side, we have the predicted. So this is the model, right? So this is the model. And what does the model predict? Given a sample, does the model predict that it is positive? Okay, if the model predicts that it is positive, and it is in fact positive, that's called a true positive. Okay. Now, if the model predicts that it is positive, but it is actually a negative, labeled as negative, that is called a false positive. Okay. Then on the other end, if the model predicts that it is negative, right? If the model predicts that it is negative and it is in fact positive, then that is called a false negative, because it predicted it is negative, but it's false. And of course, if it is negative and the model predicts that it is negative, that is called a true negative. Okay, so that's basically the terminology. And then here we can think of the equation for calculating recall. So recall then, just like we saw before, will be where the numerator is true positives, right? So true positives, this one. So it's true positives. And then the denominator is true positives plus false negatives. So this one, right? So out of the actual, right? Out of the actual, how many were actually positive? Okay. And that gives you the recall. So out of all the actual for that class, how many actually were that class? Okay. Predicted basically. So here we can think of it in terms of the terrorist example, right? So now if we look at this part of the equality, we can say that out of terrorists correctly identified by the model, right? That's the numerator. And then the denominator is terrorists correctly identified by the model plus terrorists incorrectly labeled as not terrorists. Okay, so the model then, they were terrorists because it says terrorists incorrectly labeled as not terrorists, which means they were terrorists, but the model said they were not terrorists. Okay, and that's a bad thing, right? That's a bad thing because ultimately you would want to capture the terrorists, or if this was, cancer, you want to capture that or detect it, right? So that's the idea with recall. Okay, that's the idea with recall. Does that make sense, guys? Okay, so I'm not hearing any questions.
Yeah, makes sense. Makes sense.
All right, so here's the sort of the definition there. So true positives are data point classified as positive by the model that actually are positive, meaning they are correct. Oh, sorry, this is this I've already defined, so all of this is defined. And then, as I said, and here it's written, true positives are correctly identified terrorists, and false negatives would be individuals the model labels as not terrorists that actually were terrorists. So recall can be thought of as a model's ability to find all the data points of interest in a data set, okay? Which is true, right? Out of all the actual, right, we found that. So we want this to be high, okay? Because recall can be thought of, and this is an important definition, recall can be thought of as a model's ability to find all the data points of interest in a data set. Okay. Now, if we look at, and here again, so how can we find all terrorists? In this case, let us predict everyone as a terrorist, right? So if we predict everyone as a terrorist, we'll definitely capture it, right? So let us predict everyone as a terrorist and problem solve. So recall will be high. The problem is, though, that as we increase that recall, we decrease precision, right? And that's a problem because, well, as we will see in a second, precision is also important. That's why the F measure is good, right? So this is one justification as to why we look at the F measure, because the F measure tries to balance both precision and recall. Again, intuitively, we know that a model that labels 100% of passengers as terrorists is probably not useful because we would then have to ban every single person from flying, right? Which is true. So remember, we had 800 million passengers, only 19 were terrorists. This doesn't work. So just making everyone a terrorist doesn't work, even though our recall will be 100%. Okay? So this approach would suffer from low precision or the ability of a classification model to identify only the relevant points. Okay, so that's really the issue here. So terrorists correctly identified. So here, this translates to 19, 19, and 0, right? When we have high recall. So that would be really high, but that's not going to work for us. So let's take a look then at precision now. Precision is the other one. And again, these two are important metrics to look at. F measure usually is a combination of the two, so it might give you a little bit of better information. So let's think about precision. Again, we look at the table. So we will look at our table just as we were looking at it before. We do the precision here. And now we can think. Precision is where we have on the numerator the true positives. Let's take a look at that, true positives. That's the precision. And on the denominator, we have the true positives plus the false positives. So this one, right? So out of the rows, Oops. So out of the rows and then that portion. That's precision. All right, so that basically means out of all the actual, how many did we predict correctly, right? And so here we can see that. So this would translate into true positives, not numerator, denominator is true positives plus false positives. So if you think about it in terms of the terrorist problem, this would mean the terrorist correctly identified as terrorists, right? That's the numerator. And then the denominator is terrorists correctly identified plus individuals incorrectly labeled as terrorists. Okay? So because the model here just will say these, right? So all the positives here, and then how many were actually here and how many were actually there. So that's going to be individuals incorrectly labeled as terrorists. So precision is defined as the number of true positives divided by the number of true positives plus the number of false positives, okay? Which is that. So these two are the denominator. False positives are cases the model incorrectly labeled as positive, okay, that are actually negative. Or in our example, individuals the model classifies are terrorists as terrorists that are not. So, you know, somebody that is innocent, basically. Precision expresses the proportion of data points our model says were relevant and actually are relevant, okay? So in this case, we have, so that's basically the idea with precision. So now we can see that our first model, which labeled all individuals as not terrorists, wasn't very useful. Accuracy, okay? Although it had near perfect accuracy, it had 0 precision and 0 recall because there were no true positives. Now, if we modify the model slightly and identify a single individual correctly as a terrorist, now our precision will be 1. No false positives, but our recall will be very low, okay? Because we will still have many false negatives, okay? So you have to play with that a little bit. If we go to the other extreme and classify all passengers as terrorists, we will have a recall of 1. False negatives equals 0. We'll catch every terrorist, but our precision will be very low and will detain many innocent individuals. And so that's really the little game that you're playing with these things, right? Do you miss many or do you catch all of them, but they're just basically drowning by the noise. So in other words, as we increase precision, we decrease recall and vice versa, okay? And so that's really the problem with the two metrics, but they do provide a lot of intuition for our problem. So the better solution, or that's why this justifies the reason why it's good to look at what is called the F measure. Right, so the F measure is a combination of both the precision and the recall. Think of it as it just finds like an optimized result between the two. All right, and intuitively, we just have to think as, okay, if we get a good F measure, then you know, our model is good. So we would want on a 2-class problem, you know, an F measure of like 65 and up, 70 and up, you know, it just starts to get better and better. So in some situations, now there are valid situations where you just want recall to be high or precision to be high. Depending on what you want in those situations, you kind of have to go back to these slides and really think, right? So it'll you know, adapt it to your problem. You know, look at this and kind of figure out, okay, which one of these do I really want? Do I want precision? Do I want recall? Right, so you'd have to analyze. But in generally speaking, you just focus on the F measure, okay? You just focus on the F measure. And so in some situations, we might know that we want to maximize either recall or precision at the expense of the other metric. So for example, and this is where this becomes intuitive, right? in preliminary cancer screening of patients for a follow-up examination later on. So basically you have like 2 exams. One is an initial scan, and then, you know, we would probably want a recall near 1, you know, a really high recall. And the intuition there is that we want to find all patients who actually have cancer. And we cannot accept a low precision, and we can accept a low precision if the cost of the follow-up examination is not significant. All right, so it's basically like we want to find, we don't want to miss anyone. So even if this is like this, you know, we want to find all of them and not miss any potential candidates. So if this is, obviously this depends on resources, right? So if you have limited resources, you might have to do something like that, right? Where you miss some, but your resources only allow for this number of people. However, if your resources allow for everyone, you extend basically the pool, even though you have a lot of cases that you're going to discard, but you don't miss the target here, because obviously that means human life, right? So that, you know, that's kind of the intuition there. Does that make sense, guys? This idea intuitively?
Yeah, no, it makes sense.
All right. So we can go back to this. So that's why I'm saying, right? So that's why you really need to understand. I don't expect you guys to get this, you know, like right away, like, okay, what is recall precision? It's important to understand the reason why you have these metrics, and that if you ever have a problem, you don't just, oh, I'm just going to go with the F measure. Definitely the accuracy. I almost always say the accuracy is not a good indicator of anything, right? So don't look at accuracy. You look at precision recall on a per class basis, actually, which is one of the things we will look at shortly as we look at WEKA. So, but the idea is that sometimes precision might be the thing that you want, or it might be recall. So this is an important paragraph. So let's take a look at it again. So for example, in preliminary cancer screening of patients for follow-up, right, examinations, we would probably want a recall of 100%. 1 just means 100%. So because we want to find all patients who actually have cancer, and we can accept a low precision if the cost of the follow-up examination is not significant. So again, you know, we can afford this as long as we find that. But in some other situations, the resources just wouldn't allow for that, right? So that's why people have to come up with all these things, all these other tricks. However, in cases where we want to find an optimal blend of precision and recall, we can combine 2 metrics using what is called the F1 score, okay? And that's the next metric, which I always think for supervised learning is one of the most important ones. So the F1 metric is basically, now intuitively we would know that it is a combination of calculating precision and recall, running it through this equation, and then we have our value. So the F1 score is what is called the harmonic mean of precision and recall, taking both metrics into account in the following equation, okay, in the following equation. All right, so that's the idea, basically. Okay, so let's take a look at the F1 measure. So we have precision and recall. So we use the harmonic mean instead of a simple average because it punishes extreme values. So that's really the key with this equation, right? Think about it. It punishes extreme values. So that is, you know, intuitively, that would be when, you know, precision, and recall, right? We have the 2 metrics there. So if this one is 1 and this one is 0, or if this one is 0 and this one is 1, those are what are called extreme measures, right? Because it's got really great recall but terrible precision, or it's got really good precision but terrible recall. It didn't find a balance. So a classifier with a precision of 1 and a recall of 0 has a simple average of 0.5, but it would have an F1 score of 0. You see that? It would have an F1 score of 0 if you think, because, 0 times 1, 0, right? So basically it gets, punished in a sense. The F1 score gives actual equal weight to both measures. Okay, so that it kind of, that's why it's combined. There are other metrics for combining precision and recall also, such as the geometric mean of precision and recall, but F1 score is the most commonly used. And this you'll find in a lot of the reports, papers, etc. F1 measure is always a combination of precision and recall. Right. If we want to create a balanced classification model with the optimal balance of recall and precision, then we try to maximize the F1 score. And that's why what this means is that when you're doing your model, you're creating your model, you're creating your features, you're running iteration after iteration, you basically, the metric to kind of optimize is what is called the F1 measure. Okay? Questions, guys, about that? Make sense?
Yeah, it makes sense.
All right, so to wrap up then with the slides, so performance evaluation, basically we've looked at precision, recall, accuracy, precision, recall, the F measure, and the confusion matrix. The evaluation of performance of your classifiers is extremely important. You can use the sklearn kit for this. It provides really good modules to address this issue. In particular, the evaluation often involves measuring, and I'll give you a function that basically does all of these together. And the best way to understand these is to think of the confusion matrix, which is what we've discussed in the slides, which I've already described what the confusion matrix does. And then here's the code, okay? So this function you can literally just copy paste into your code going forward. So I suggest you do that. This is very similar to the accuracy one, right? So it took Y-test and Y-pred, right? So it takes those. This is just the algorithm name. You can disregard that. So like if you want to say, oh, these are the results for naive Bayes or whatever. Keep in mind this, when I wrote this some time ago, I used Python 2.7. Now in Python 3 and above, the print is done like this. Okay, so just keep that in mind. I think here I have some places where I forgot. See, some prints have the parentheses, but not all of them. So make sure you make that adjustment. Okay, but basically it's pretty straightforward. This just prints the algorithm name, so you can literally just get rid of that if you don't want it. Now you need sklearn, and from sklearn you call accuracy score, right? And you provide Y-test and Y-pred, and that's it. Everything else is just a print statement. For the confusion matrix, you have to write this code like this. So I suggest you just copy paste it. It basically calculates the confusion matrix. You can see that there. It calls confusion matrix with Y-test and Y-pred. This is just a print statement, so you can get rid of that. Then it prints it, and then it also prints it as a pandas. This is just a little pandas magic to kind of give it better formatting. Okay, so that's really all that pandas does here. Is it uses crosstab with Y-test and Y-pred to provide a little bit better presentation. Then you have precision here, you have recalls here, and you have F1. And these are the modules that you import. So when you import the sklearn.metrics, you will import these metrics here. Okay? So this function, this code, you can just use as is. There's plenty of examples of this code also in my GitHub, so you can just get it from there. A lot of the function, because I use this in all the code examples basically. So every time you now, instead of just calling that accuracy function, that we had defined in previous examples, you can just use this function every time. Okay? And then I've already explained this. You can take a read through it. And that's it. So that concludes the slides for today. Remember, we were covering performance metrics. Now, what we're going to cover is the WEKA lab, which is actually so easy that we can cover it in just 30 minutes. All right, so let me go ahead and stop sharing here. Okay, and now I'm going to go ahead and go to the website, so the course website. So let me share that. Okay, so this is the course website that you should be seeing. Let's go to the course, Machine Learning Foundations. Okay. And if you scroll, there's a couple of things. Let me get some coffee. Just give me a sec. So WEKA, this link here, click on it. All right, and this is the tool that you need to download. All right, so as I was saying, this is the tool. WEKA is a tool made in New Zealand that has been around for a very, very long time. So you can see here, it's got a lot of things. You can download it. And that's what I suggest that you should do. Download it. It can do deep learning, although we're not going to use it for that. You can access WEKA from Python, Spark. So when you guys take Professor Kim's Hadoop and Spark class, hopefully you'll take a look at that. So it's a very powerful tool, and I'm basically not going to do it justice, okay? I want you to, I have a great respect for WEKA, and I will not do it justice in showing all the tools of it, but I will show a little bit. If you notice, I think in this course, one of the books that I suggested is actually this book. So data mining, practical machine learning. They're up to the 4th edition. It's got a nice owl there. So if we go back to the course website, you can, I believe, yeah, practical machine learning, Whitten and Frank, so the latest edition. So that's one of the books. It's a great book, great book. If you want to learn WEKA, we're mainly focusing on this book, but this one also, in my knowledge comes from this one also because I've read that book thoroughly. So anyway, these are great books. So what you will need to do is go to that site, the WEKA site. So hopefully by now, obviously you installed Anaconda, and that's what we've been using so far this semester. WEKA is, as I said, it'll be a calculator if you want to think of it that way. So whenever we're looking at algorithms, you run your own algorithm and you compare it to the WEKA result. So you did KNN, now you can run data on your KNN algorithm. You should load data from a file and run it through your algorithm and then run it in WEKA as well. Then do the same with the naive Bayes. Both of those algorithms are there, and there are a few other algorithms that we will learn later in the semester that you can always compare to WEKA. So WEKA is a really good benchmark or baseline to compare your results. Okay, so your homework is to download this program if you haven't done so already. Download it to your environment. And also for the homework assignment, you guys will need these 3 files. So see here in datasets, right? In datasets, you will need Fisher's Iris, which is the Iris dataset that we've been talking about. You can download it there. And also the MNIST dataset. I have it broken up into train and test. Sometimes students' computers don't have enough power, so they end up just using one of the 2 instead of both. So that's perfectly fine. these are the two classic data sets for machine learning. Iris is 150 samples, 4 features, 3 classes. And MNIST is from images. So Iris is from plants. The 4 features are like, you know, length of sepal width, sepal height, you know, and things like that. MNIST is handwritten digits, so it's images. I strongly recommend that you look up Fisher's Iris and MNIST on Wikipedia or something. Take a good read of what the data sets represent. But I can tell you they're just handwritten digits of numbers. MNIST has, I think, 70,000 samples. 60,000 are for train, 10,000 are for test. The images are 28 by 28, so when you spaghettify them, you take a 2-dimensional array and make it into a 1-dimensional, you end up with 28 by 28, which is 784. So MNIST ends up being an X of, let's say, 70,000 samples by 784 columns, okay? And it's got, for every pixel out of the 28 by 28 images represents a feature. So it's 784, and then it's got 10 classes, because obviously there are 10 handwritten digits, right? 0, 1, 2, 3, 4, 7, 8, 9. There's no 10, so it's just single digits. Usually what it is let's say that, you know, all of us in the class, you know, you write a 2, I write a 2, you write a 5, I write a 5. We all have different ways of writing things. And so all of that was captured in these are black and white images or grayscale, right? So the values in the pixels are from 0 to 255 grayscale. All right, so those are the data sets. So you will download these data sets. And basically the next homework, the WEKA homework, will be to run these data sets in WEKA. So basically do what I'm going to demo in a second, okay? What I'm going to demo in a second, how to use WEKA and everything. I have already on my computer downloaded Fisher's Iris, okay? So I have Fisher's Iris on my computer already, and I also have WEKA installed. So I'm going to go ahead now and start WEKA. Questions before I begin, guys? Questions?
No questions.
This is like the easiest you can do machine learning. But it's very powerful. I don't want you to think that it's not powerful. All right, so let me go ahead now and first of all, I'm going to start WEKA. I need to share that. All right, so I'm sharing a window. Hopefully you're seeing this little window that says WEKA. It's got that little bird. Then you click on Explore, this button. It's got all these other options, and you know, when we look at other things, we'll come back at least to Experimenter. But for now, let's just click on Explore. So you click on that, and then it opens another screen, and I need to share that one.
Professor, we
Yes?
can't see the other screens. We can only see, oh, there it goes.
You can see it now, correct?
Yeah.
Right, so when I clicked Explore, you should see this, right? Okay. This is the main screen, okay? And it's got basically the way it works. This is written in Java. Java is not one of my favorite languages, but it's written in Java. But this has, as you saw in a second ago, there is a Python way of getting into WEKA now. It's got basically these tabs, which are not, they're not shown right now, these tabs, but these are the tabs that we can use for everything that we want to do. So the first thing you do is usually you load a data set by opening a file. You could also get a URL, a database, or generate random data. It's got this idea of filters, and these filters are basically like when I say to you guys, you must always scale your data, right? So you would use these filters for that, but there's many other filters in here. Okay, so that's why I said it. If you're interested in WEKA, the best recommendation I can give you is get that book, the 4th edition with the little owl, and read through it. It's very easy to read, and you know it'll give you all the power of WEKA. But I'm just showing you enough that you can, you know, get a feel, because this is usually the pipeline that I do. This is my pipeline. Whenever I do a project, you know, I run my data through here. So the first thing, and then here, there's all these screens that are currently not populated, but they will become populated in a second. So the first thing I'm going to do is I'm going to load my iris data set. So I'm going to click on Open File, and then it opens another window. So this really likes opening windows. Are you seeing that new window, guys, or no?
Yeah, we can see you opening the file.
You can see it, right? You can see, okay. You're seeing me, okay, so here the first thing you have to do is file type. So click on that. There's a lot of types, but you just simply click on all files. And I have selected my file to be CSV. So, or created. The files that you will download, I believe, are CSV. So then the ones I showed on my website. So then you click on here and you go, I'm going to go to my desktop, which is where I have my data. Right, and then you can see I have all these files in here. I have one called iris.csv, right? So I'm gonna click on this one, iris.csv, there, right? And then I'm going to you know, oops, sorry. Click on it and then click open. And you see now the data has been loaded, right? So the data has been loaded, and now the windows, it's like they're alive, right? So the windows are alive. So what do we have? We have, Iris has 150 samples. You can see that here. You see my mouse. It's got 5 attributes, including the class, right? So here they are. These are the features. 1, 2, 3, and 4 are the features, and 5 is the labels. So if I click on these, it basically on this side here, it kind of gives me like the minimum, the maximum, the mean, and the standard deviation, kind of like what we did with the NumPy example, right? So, or sorry, with the naive Bayes, right? So same idea. We talked about all of that. Here it gives you that information. Notice one thing that's important: the features usually should be numeric, the type. Numeric over here, but the class needs to be nominal. Okay, if it's not nominal, none of these will work, okay, appropriately. So if you ever have a data set that you load and this one, the species does not say numeric, but instead it says nominal, sorry, it doesn't say nominal, instead it says numeric, but it's a classification problem, you're going to have to go to the filters, click on choose, then you're going to click on filters. I think it's unsupervised, and then attribute. And then you need to look, there's a lot of filters in here, but you would need to look for numeric to nominal, this one. You see that? Numeric to nominal. What happened? All right. There it is. Numeric to nominal. You see that? And then you have to click on the white space here. Click on that. And then you need to say which attribute you wish to convert. So instead of converting first to last, that means all, you would just say 5. Because 5 is species. And that's the one that you want to convert from numeric to nominal. Then you would hit OK. And then you need to hit apply. When you apply, it'll convert the data. Currently, mine is already nominal, so I don't have to do it. But that's usually a problem students have in the past that I've noticed, so I wanted to point that out. Okay? Once you look at the data here, you can take a look at all the values, and you can see, for instance, the features in sepal width. They go from 2 to 4.4 to 4.4, where the mean is 3.05 and the standard deviation is 0.34. Now, these are not scaled yet, but if you look, they're very consistent. So there's no really one feature that will dominate. However, it would still be recommended that you scale the data. Okay? If you look at the species, you can see here there are 3 classes, Setosa, Virginica, and versicolor. Usually, I don't like to put words in the classes. I always do like 0, 1, 2. However, WEKA is the only program that will allow you to put the words in there, only for the labels. And then you can see that there's 50 of each, right? So and you can see them here, the blue, the red, and the light blue. It's a highly balanced data set because every single class has the same number of samples. And MNIST is also like that. They're also balanced, and that's why they do really well. So here, accuracy would be an okay metric, but keep in mind, in imbalanced data sets, real world data sets, it's going to be much more of a challenge. Questions so far, guys?
No questions.
It's all making sense. So as you can see now, now what can you do with this? So for now, we're basically just covered supervised learning and classifiers, right? So we're going to classify, and for that, we're going to go to this tab. So you can see there's a little tab over here. I'm going to click on that one, and there you go. Now I got my data. So this one is just for loading the data, filtering the data. You can also look at the data. Look over here. It's got a little edit button. Press on that. There's your data, your beautiful data, right? So you look at it. You can see everything about it. And so that's very interesting. It's got all the 4 features, the classes, Setosa, versicolor, Virginica. So definitely a great tool. Now that we have our data loaded, let's go ahead and click on classify. And now here are the algorithms. Now, usually, as so far in this semester, we are 6 weeks in, and we've covered 2 algorithms very thoroughly, KNN and naive Bayes. Remember, you already submitted your KNN homework. The naive homework has already been discussed today, and it's due a week from today. And then this WEKA will be due 2 weeks from today, right? It's a new homework assignment as well, but it's pretty easy. Just download the IRIS and MNIST data sets that were supplied in the website and run them through this, and basically just do everything that I'm gonna do. So it's pretty easy. I just want you to kind of get a feel for it. So how does it work? All right, so you click here on choose, and you're gonna select your algorithms, okay? So for instance, the first algorithm we learned was KNN. So that's in Lacey. You click on Lacey and you click IVK. And that's it. This is your KNN, K nearest neighbor algorithm. Okay, then you have 2 options. You can do the percentage split, just like we did with sklearn, train test split, right? Split 70%. So 70% will be used for training, 30% for testing. Notice the label here is species, the nominal one. That's the class. That needs to be the target. And then you just hit start. And boom. There you go. Done. Now you look at the output, and you can see here, today we discussed precision, recall, F measure, right? And those are the exact same 3 metrics. Here's your accuracy up here, and you have your confusion matrix. Okay, so we can take a look at the results. So for instance, the precision is, and notice that the precision is given in 4 ways. It gives you one for the last row is for everything, right? So overall. And then you have on a per class result. So you have Setosa, what was the precision, versicolor, Virginica. So for instance, it's really good for most except for versicolor. For versicolor, the precision is the lowest at 0.88. Recall, on the other hand, notice that there's a trade-off, right? So the recall here is lowest for Virginica. But overall, it's pretty good. Now, if you look at the F measure, which is a combination, you can see that it's pretty good. Above 90 for all. Does that make sense, guys? These are whenever you look at your results, you will look at these 3, okay? Plus you have your 95% accuracy over here. And then if you look at the confusion matrix, just like we discussed, out of Out of the 14 that were A, how many were classified as A? 14. That's good. Out of the 16 that were B, how many were classified as B? That 16 as well. That's good. But in the Virginica category, out of 15 that were C, 13 were correctly classified as C and 2 were misclassified as B. All right, so that's what the confusion matrix tells you. Okay, so it's pretty useful in that sense. Now today we also talked about sometimes you want to do 10-fold cross-validation, right? So you can click on this button here, and then when you do that, now you can just run it again. So you can click on start, and this one is a little bit more thorough. Notice that here the values actually went up because it did it 10 times, right? It did it 10 times. However, look at the confusion matrix. I would say this is more realistic of misclassifications, okay? Because it did it 10 times instead of just one. It randomized the data as we described how the cross-validation works today, okay? All right, now if you ever have a data set where you have a train set and a test set, you use these two buttons here. So first you would click on use the training set. So you have to load it here with pre-process. You would train the model. Then you need to, when the model's trained, you get the model's here, right? This little blue thing. Then you would click on this. You would click on that and kind of load the test set from this by clicking set. And then once you've loaded it, you right click on the blue. So you right click on the blue, and then it says something like reapply this model or something like that. Okay, reevaluate model in current date, in current test set. Actually, it's the item that's not highlighted because I don't have a set there. But if a set was there, it would be that one. Reevaluate model on current test set. That's it. That's basically the pipeline. Pretty easy, really. Is this clear for everyone?
Yeah.
All right, good. So now, what was the name of the next algorithm that we looked at? We looked at naive Bayes, right? So we also have naive Bayes. You click on Bayes here, and then there it is, naive Bayes. Click on that one. Again, make sure the species is the category. Click start. Boom. Now this data set obviously is very small, so it does it really fast. You know, when you do this with MNIST, it's going to take longer. Okay, it's going to take longer. But you can see the results here again with naive Bayes, precision above 90, recall above 90, so an F measure above 90. So all pretty well, pretty good. All right, now a few more algorithms, right? So, you know, what are some of the other algorithms that are important in this course? Well, trees, right? Decision trees. So the J48 and the random forest, right? So these two are algorithms that are important in the category of trees. If we have time this semester at the very end, I want to cover decision trees. So you would click on J48, and that's really all you have to do. Make sure this is, let's switch back to percentage split 70%. Click on start, boom. And you can see the results are low, 88, again, 86, but that's only because I'm using, if I use cross-validation in trees and then hit start, boom, they go up and they become better. You see that? That's decision trees. If you want to try it with random forest, you click random forest over here. Obviously, if a tree is a model, a random forest would be a model of trees, right? That's the intuition. Again, 10-fold cross-validation, nominal species, hit start. And boom, done. Precision, recall, F measure, and accuracy over here, which is the metric that you knew about up until last week. Now you know of all these other new metrics. Okay, a few more. Let's see. Bayes, we're just from these, we're just going to cover naive Bayes. From functions, multi-layer perceptron. So this is where we're going. Logistic and simple logistic and multi-layer perceptron. This is where we're going, you know, right around like week 8 or 9, we will get to this. The multi-layer perceptron is a neural network, okay? So these have a tendency to be very powerful, but also very slow in WEKA. So I'm going to hit start. And notice this one took a little bit longer, right? But this is, if you're following along and you did this, you've basically run your first neural network, okay? By running the multi-layer perceptron. But we will, obviously, that's one of the main topics in the course. So we will cover it in NumPy in about 3 weeks or so. We'll begin that discussion. And of course, the multi-layer perceptron is the ancestor of deep learning, right? So not like a very far in the past ancestor, but just a direct step towards. So we need to start with multi-layer perceptron to understand deep learning. Okay, so there's that. That's another algorithm. SMO, I think that's the support vector machines, but there is a support vector machines algorithm. You just have to download it. So there, at the beginning, when you guys start WEKA, there's going to be something that says, hey, I'm the program manager or something. And that option allows you to download other algorithms that are not by default in this, like support vector machines. That one, unfortunately, I don't think we'll have time to cover this semester. We've covered lazy algorithms like KNN, which is IBK. And then there's a few other ones in here. I don't believe we'll be covering many there, you know, and so on, right? So we'll definitely come back to the ones based on functions like multi-layer perceptron neural networks and logistic regression. Linear regression, you can see that there when the data is numeric. When the data is numeric. So now that I've done this, and you know how to run the classifiers, the last thing I want to cover today, which believe it or not, in 4 minutes we can cover, is feature ranking. So what is feature ranking? Feature ranking is when I want to select my features. Let's say that in the iris data set, right, I have 4 features, but for whatever reason, I can't collect, you know, because I have to go out into the forest and I have to hire, you know, hundreds of people to go into the forest to collect information about these trees, right? And I just don't have the budget for that. So I need to cut down like one feature, but I don't know which one. Well, the machine learning algorithm can tell you, and that is called select attributes. So if you click on the select attributes tab, right? And then now in here, you can select cross-validation or use full train set, either one. I would suggest you pick both. And then you hit species, right? The class species. And then now you select the method. So what you want is you want to rank the features. And then this just says, which method do you want to use for that ranking? Just use the suggested one, information gain. So click yes. So information gain is the algorithm that it'll use to rank. And now you can just go ahead and click start. And boom, done. So when you look at this, it's telling you the ranked attributes. So it's saying that out of the 4, petal length, petal width, and sepal length are the most important. Sepal width is the least important. So if you have to, now it does contribute. It's not 0, right? So it does have a contribution, but it's not a contribution like 1.4, which is much higher, right? So if you have to cut out one feature, you can cut out this one. And that is called feature ranking. Now, this is important when you have thousands of features, right? And let's say you have so many features that you tried and your model just, you don't have enough RAM on your computer. Well, if you run this, it might say, you know what, you can cut out these features. So you just cut them out. And that's called feature ranking. And that's basically it. Now, this is not the same as dimensionality compression, right? That's what we're going to cover next week with singular value decomposition. So this is just feature ranking. You can think of it as selecting attributes. We're going to take some features and just drop them completely. Feature transformation, what we're going to look at next week with singular value decomposition, is different in the sense that they're the features. We take all the features and kind of use all the features to create new features. So every new feature has a little bit of all the original features, but we still lose information in a similar way as feature ranking, but they're different. Here, we drop one feature and we just use the rest. In feature transformation, we create a new feature, alpha, let's say, which will be a linear combination of the initial 4 features. Okay, so just keep that in mind. But that's, you know, the topic for next week. So feature transformation is actually pretty important, and it leads to a lot of things like feature transformation, dimensionality reduction, and also recommender systems, right? So it's all a very important topic that actually takes us to the recommender system, which, you know, you can't, you know, if you work in a company of any kind, you know, a recommender system that sells products, a lot of products in particular, like a supermarket, you know, as you know, a recommender system is going to be crucial to maximizing your business, making more money. You know, recommender systems, which is coming up next week, is like, you know, remember the classic marketing example of diapers and beer, right? So they noticed that, you know, fathers were coming in to the supermarket to get diapers, and they figured out, well, what else can we sell them? So they put the diapers next to the beer or someone along the way. So the parents now, before they just came for the diapers, now they come for the diapers and they see the beer and they're like, oh yeah, I'm going to take the beer as well, right? So that's kind of the idea. That's a classic marketing example. But when we talk about recommender systems like Netflix, etc., we got to talk about that. So that will be the topic for next week. So we'll do that. But this pretty much concludes our discussion of WEKA. And then now your homework will be basically to use both the iris, basically repeat what I did with iris data set, and also repeat what I did with MNIST, okay? So I'm gonna go ahead and, so I have a couple of minutes. So first, before I finish, I guess, were there any questions about WEKA? Or was everything clear?
Everything's clear.
Clear, right? So you can always just look at the video again. Everything is there. So now let me just go back to the bright space over here. And in performance metrics, right, this little module here, I'm going to create the new assignment. This one will be, since the naive base is due a week from today, right? I already described that with you guys just now. Now this one will be due 2 weeks from today. So new assignment, pretty easy. Just get a feel for WEKA. So let's call this one homework WEKA. So this will be due the 3rd by 10 p.m. And stay open until the 6th March. Using WEKA, analyze the iris and MNIST data sets provided in the course website at, you know, my website there. All right, so just download the 2 data sets that I showed you. Basically just do what I did, you know, kind of do like the demo that I did of WEKA, just repeat that whole process. So perform classification with several classifiers and feature ranking. report your results. Is this clear enough, guys?
Yeah, it is.
All right. Perform classification with several classifiers, naive Bayes, KNN, multi-layer perceptron decision trees, right? So that's a few. And feature ranking and report your results. Okay, so it seems like everyone gets it.
Oh, I do have a question. Did you want us to do the 10-fold or did you want us to do the 20/80 split?
Do both. You know, what I want you to do is to practice really, to kind of get a feel for, so do everything that I did in the demo.
Okay.
Sense? Yeah. All right, so you have 2 homework assignments. I think they're pretty straightforward. Naive Bayes one, run through that data set, and then the performance metrics. The only thing that's missing, I think, from the algorithms is for me to show you how to easily load iris and MNIST into your KNN and naive in NumPy, but we'll do that in the next class. And then next week, if you want, you can, oh, there's nothing there yet. Okay, I haven't loaded materials, but we'll be covering these 2 modules Monday. We'll start with them. All right, so I'll stay for a couple of minutes if you guys have any questions. I'll stop the recording now.